Welcome to video 6 on factorising polynomials. This particular video focuses on higher order polynomials. Now first we should note that examiners will very rarely set examination problems that are algebraically awkward just for the sake of it. Okay? They're more interested in processes and students demonstrate they understand what they're doing. Consequently, if you need to factorise something higher order than a cubic, it could well be that several of the roots are obvious and you are expected to spot this before resorting to any difficult algebra. If you haven't spotted any obvious roots, you've probably missed something. Now, there's no generic guide here. Basically, it relies on experience and common sense. You need to spot shortcuts by trying the obvious first. But what is obvious will vary with each problem and each context, and if you read the question, again, it should be obvious. So, we'll start with an example of how you might spot the obvious. So I'm going to give you a polynomial p of k, and your job is to find the factors and the roots. Well, here's p of k, and you'll notice it's quartic. K to the 4 plus 10k squared plus 16, and you might think, golly, it's quartic, how do I start? However, this is clearly quadratic in the variable k squared. So what I'm going to do is get rid of k squared and write this in terms of a new variable w, where w equals k squared, because that means I have now got a quadratic in w. And clearly, once it's a quadratic, I can solve it. Okay? Now the interesting thing here for this particular problem is if I solve this quadratic, and I've put the solution down here, you'll see I get p of w equals w plus 2 times w plus 8, and that implies that k squared equals minus 2 or k squared equals minus 8 are the roots. And you'll realize, of course, that you do not get real values of k as a solution to this. So I've written down at the bottom the actual solution. You've got 4 imaginary roots. However, just to summarize, the key thing about this slide is you started with a quartic, but actually solving for all 4 roots, as can be seen here, was a relatively simple process. Okay, example number 2 for spotting the obvious. So now we've got a different polynomial. Here it is, another quartic. Z to the 4 minus 5z cubed minus 7z squared plus 41z minus 30. Again, you're looking at this thinking, where do I start? Well, you remember we were given a hint before. If you can't see anything really obvious, then try simple numbers like plus or minus 1 and plus or minus 2. So that's what I'm going to do next. I substitute in 1. There it is, b of 1, and I evaluate b of z at z equals 1, and what do you know? I get 0. So z equals 1 is a root. I try minus 1, and I substitute that in, and you notice I don't get 0, so minus 1 is not a root. I've tried z equals 2. Substitute that in, and again I get 0, so z equals 2 is a root. So you'll notice, with some very simple algebra and just guesswork, I've identified 2 of the roots extremely quickly. So b of z has got factors z minus 1 corresponding to the root at 1 and z minus 2 corresponding to the root at 2. How do I find then the last 2 roots? Well, I'm going to need to do a long division. Now we'll give a summary of the long division here only, just to get you started. It's a different topic which I'm not intended to cover in this video. So I start with my original b of z, there it is, z to the 4 minus 5z cubed minus 7z squared plus 41z minus 30. However, I know this has got a factor z minus 1 and a factor z minus 2, so I can rewrite it as z minus 1 times z minus 2 times a quadratic factor, which here I've put down as z squared plus az plus b. Step 3 then, I multiply out these 3 factors. And that's what I've got when you get down to step 4. You see what you get. Z to the 4 plus a minus 3 z cubed plus b minus 3a plus 2 z squared plus 2a minus 3b times z plus 2b. And you remember from the previous slides that what we can do now is we can simply match coefficients. So this blue term matches this term. The z squared term here matches this term. The z term here matches this term. And the 2b term matches this term. So if I do that, here are the equations you end up with. A minus 3 equals minus 5. So you can get a from that. A will be minus 2. B minus 3a plus 2 equals minus 7. 2a minus 3b equals 41, and 2b equals minus 30. And if you check all those equations, they should be consistent, otherwise you've made a mistake. You'll see you get a equals minus 2, b equals minus 15, which tells me that this quadratic factor is z squared minus 2z minus 15. Okay? So you should, by inspection, be able to write that gives you z minus 5 times z plus 3. So there we've got our other two factors. Alright, example 3. Now this is a different type of problem, the type that maybe appears in control engineering. So I'm now going to have a variable in my polynomial, and that variable is k. But what I'm told is that my polynomial has got roots on the imaginary axis. And it says, given that observation, can you find k and factorise the polynomial? So here's my polynomial. P of s equals s cubed plus 3s squared plus 3s plus 1 plus k. So the first thing to do is read the information in the question. What does it mean when it says I've got roots on the imaginary axis? Well, that means I must have a root at j omega and a root at minus j omega, where at this moment I don't know what omega is. So I'm going to put that factor in to the polynomial. So here we go. I've got a factor s squared plus omega squared, which gives me the two roots on the imaginary axis. Because p of s is cubic, I've only got one factor left, so I've called that s plus a. And now I'm going to multiply out p of s by multiplying these two factors, and this gives me this expanded form, s cubed plus as squared plus omega squared s plus a omega squared. And again, as in the previous slides, I can match this quadratic term with that quadratic term, this linear term with this linear term, and the constant term with this constant term. So I've got some simultaneous equations which will allow me to solve for a and omega. So here we go, equating those coefficients. This is what we get. A equals 3, that's from as squared equals 3s squared. Omega squared equals 3, that's from omega squared s equals 3s. And a omega squared equals 1 plus k. And therefore I end up with k equals 8. Right, one final example. And this one looks a bit more tricky. Factorise the following. F of x equals 2x cubed minus 6x squared minus 50x plus 150. And you might look at that and you think, oh golly, I'm not sure. The first thing I'm going to do is make it monic, because if we make things monic, it makes life easier. So there we go. A monic one is x cubed minus 3x squared minus 25x plus 75. And the key thing now is I see this 75. And I know that that last coefficient is the product of the roots, with a plus or minus depending upon the order of the polynomial. And 75 has got some obvious factors, 3 and 5 being the sort of ones that jump out at you. So you might say, well, let's try 3 and 5. I'm not going to bother with 1, 2, 4, things like that. Let's try 3 and 5, because I might get to the roots very quickly. So here we go. I substitute in 3, evaluate f at 3, and what do you know? I get 0. I substitute in x is 5, and what do you know? I get 0. So what I've determined very quickly is that I've got an x minus 3 and an x minus 5. Okay? Two factors by inspection. So the last root can be determined using the product of the roots is minus 75. Now, if I've already got a root at 3 and 5, the last root therefore has to be at -5, which means I've also got an x plus 5. Now you can multiply out those three factors and confirm that it does indeed give you f of x. So some final reminders. If the roots cannot be identified with some simple checks, then you shouldn't be getting it in an exam, and I would get the computer out and use an appropriate package. Spotting the obvious develops good engineering insight, which can help in design, but there's little benefit in doing complicated algebra on paper just for the sake of it. So certainly, if you ever had me as a lecturer, if you've got an example that looked quite complicated, you should be thinking, there's something obvious in here, I shouldn't be doing really difficult algebra. Now, just a final note, readers will note when I say polynomial division, I don't actually use long division. I think it's far easier to multiply out and equate coefficients. But if you want to do it another way, then feel free.